So in the previous lecture, we saw the statement of the first law of thermodynamics. That during a thermodynamical process, that is a process in which there is exchange of heat and or mechanical work to change the state of a gas, the net work done, or rather the net heat supplied to the gas, is equal to the change in internal energy of the gas plus the work done by the gas. Okay. And more importantly, from kinetic theory of gases, we had seen that the average kinetic energy per molecule per degree of freedom was 1 by 2 kT. So therefore, the average kinetic energy per molecule becomes degrees of freedom into half kT, where we understood that degrees of freedom has standard values of 3 for monoatomic gases and 5 for diatomic gases. For polyatomic gases, it's a more complicated thing, so doesn't have a standard value. And then we had seen from this relation how we can predict that the total kinetic energy of gas molecules is given by n f by 2 RT or f by 2 times PV. Okay, of course, earlier in kinetic theory of gases, we have seen all these relations. RMS velocity, these relations. So now the important thing here is that this quantity, the total kinetic energy of the gas molecules, this only is called the internal energy. U, and that then comes by this formula. So before we discuss more about the applications and the method of calculation of Q and W in first law of thermodynamics, let's look at a quick question where we can utilize this concept to understand a process. So we have already seen this in the last lecture. So if you have anything you need to discuss about any of these facts or these equations, just let me know. Otherwise, it's fine. Okay, so let's come to our example. So what is happening here is that we have two insulated chambers. So heat insulated chambers. You can think they are of like identical volume, and the walls of the chamber are heat insulated, as is the pipe joining them. There's a pipe joining them with a stopper or a valve. Let's say this is chamber A and this is chamber B. So initially, the valve is shut, okay, and chamber A has helium gas at a pressure of 3 atmospheres, temperature of 400 kelvins. Volume of chamber A is equal to volume of chamber B, is equal to, let us say, 2 liters. And chamber B, that is filled with nitrogen gas at a pressure of 2 atmospheres and temperature of 300 kelvins. Now the valve is open and the gases mix, and eventually an equilibrium state is achieved, or a steady state is achieved. So find the pressure and temperature at equilibrium. Just try out this question. So I'll give you a hint over here that what is happening is that there is no heat exchange with the surrounding, because the walls of the container are heat insulated, and also there is no mechanical work that is happening on the system. Okay, so the total internal energy has to remain conserved, or the total kinetic energy of the gas molecules has to remain conserved from the initial state to the final equilibrium state. And the other thing is you will make use of ideal gas equation. So obviously when the valve is open, the mixture of gases that will exist in container A and B will exist at one uniform pressure and one uniform temperature throughout the whole system of chambers. A plus B becomes like a combined chamber. So the mixture of helium and nitrogen gas that will exist will be at one uniform pressure and temperature in the equilibrium state. And that uniform pressure and temperature will be such that the total kinetic energy of gas molecules remains conserved, or the total internal energy of gas molecules remains conserved. So just try to apply these principles and work out this question. Okay, so hope the question is clear and the data of the question is clear to all of you. So here what is happening is initially you have in chamber A, you have PA into let's say V is equal to, okay, and in chamber B, because the volume is common, so I'm just writing this as V. So we have 3V is equal to Na R into 400, and we have 2V is equal to NBR into 300. Also we have internal energy of gas in chamber A is 3 by 2 NaRTA or 3 by 2 PA into V. So this is in liter atmosphere. And internal energy of gas in chamber B is 5 by 2 or 5 by 2 pressure into volume because it is diatomic. Degrees of freedom is 5 and this is helium. So degrees of freedom is 3. Liter atmosphere. Okay. Now from here it goes to a state where in equilibrium we have one chamber A plus B which is of volume 2V or 4 liters. Okay. Contains a mixture of nitrogen plus helium with number of moles equal to Na plus Nb at pressure P and at temperature T. So one will make use of this equation of state and the other will make use of the fact that the internal energy of the final equilibrium state should be equal to internal energy in A initially plus internal energy in B initially. So now just set up the values for the left hand side for the final equilibrium state. Okay, by writing similar terms like we have written for the initial state above. And from that you should be able to work out. Okay. So just try this out and tell me how much the final pressure will be. Okay, so you have n moles of a mixture, nitrogen plus helium, at pressure P and volume 2V. So your equation of state becomes P into 2V is equal to nRT. So P into, yeah. Now if you compare this equation with these two equations and you apply the condition that N is equal to Na plus Nb, total number of moles is conserved. Okay. So N in this equation is nRT, I mean, is equal to P into 2V divided by RT. Na in the above equation is 3V divided by 400, or first I'll write it like this, that it is equal to PA into V divided by RTA plus PB into V divided by RTB. So I have this relation that 2 times P upon T is equal to PA by TA plus PB by TB. So this becomes one equation. So this actually becomes that 2P by T is equal to, this one's initial pressure was 3 atmospheres, 400 Kelvin, plus this one was 2 atmospheres and 300 Kelvin, where P is in atmospheres and T is in Kelvin. Okay, so this is one equation. Okay. Now the second thing is this mixture will have an internal energy of how much? The internal energy of the mixture will become number of moles of helium in it into 3 by 2 RT, okay, plus number of moles of nitrogen in it into 5 by 2 RT. This is the internal energy of helium plus the internal energy of nitrogen in the mixture. It will be this, okay? So it will be 3 times Na plus 5 times Nb to R into the common temperature divided by 2. Okay, very good, Samarth. So this internal energy of the mixture should be equal to the sum of the internal energies initially. So that will give us our second equation. Okay. So we can also write this that it is 3 times Ta plus 5 times Nb upon Na times Tb upon 3 plus 5 Nb by Na. So the advantage of writing it this way is that I can write it in terms of ratio of Nb by Na. Now from the above equations, that from the equation of state, you can see slightly above over here, this was the initial equation of state. So you can see that Pa by Pb by dividing these two equations is equal to Na by Nb times Ta by Tb. So the ratio of moles is this, and this ratio was 400 divided by 300 into pressure in B was 2 atmospheres, and the pressure in A was 3 atmospheres. So this becomes 8 by 9. So Nb by Na becomes 8 by 9. So we'll substitute this here. So on substituting this here, the temperature will become 3 times Ta, which was 400, plus 5 into 8 by 9 times Tb, which was 300, divided by 3 plus 5 into 8 by 9, like this. So from this, we'll be able to find out the temperature. And once we got the temperature, we can substitute this in the earlier equation to find out the value of pressure. We'll calculate the temperature. And once we got this temperature, we'll substitute this here. And from that, we'll calculate the pressure. Okay. So just go over the steps. I'm first taking you through the steps for the first relation. That is conservation of number of moles. This is okay. So by equating the total moles N in the final mixture with the sum of the number of moles in the initial state, Na plus Nb, we got this relation between pressure and temperature. Now next up, what we are doing is conservation of total internal energy. So internal energy of the mixture should be equal to the sum of the internal energy in A initially plus B. this equation here. So this is conservation of internal energy. So this is giving us this temperature. So obviously you can see the final temperature has to be something in between the initial temperatures, which were 300 and 400 Kelvin. So it will be greater than 300 and less than 400. It's about 340.5 Kelvin. Okay. And then we can substitute that back in this equation. 2P upon T was equal to 3 by 400 plus 2 by 300. So from this we'll get the final pressure as this in atmospheres. So about 2.4 atmospheres. The final pressure and the final temperature. Okay, so this is like a more advanced application of the concepts of kinetic theory of gases. Yeah, I'll show. Okay. Yeah, I'll scroll down. So you have understood the concepts that we've used. Now, one is we have conserved the number of moles. Okay, so by conserving the number of moles, this equation here, that N is equal to Na plus Nb. So by using this, we are getting one relation in pressure and temperature. You know, the final pressure and temperature. We're getting this relation here in terms of the initial pressure and temperature. Okay. And then secondly, what we are doing is we are conserving the internal energy. Conservation of internal energy, this equation here, and that is giving us another relation in pressure and that's giving us actually a relation in temperature alone. So we are able to find the final temperature by using this relation. But to find the temperature using this relation, I also need the ratio of number of moles. So this is in terms of Na and Nb, but in such a way that I can express it in as a ratio of Nb by Na. Okay. So the ratio of Nb by Na, that is coming from the equation of state initially, the equation of state in each one. So after having got the temperature, final temperature, we substitute this in the original equation. We have used PV equal to nRT formula ना बेटा, यूज तो किया इक्वेशन ऑफ स्टेट में समझ. That also you can do. But for the final thing, na, we have a mixture. Na? So how will you take degrees of freedom of the mixture? In the final state, you have a mixture. Na? Take your total number of moles is Na plus Nb. Okay. But your total internal energy is internal energy of nitrogen plus internal energy of helium. Na? So how will you express it in terms of this has degrees of freedom 5, this has degrees of freedom 3. So you have to split it up, na? And number of moles Na and number of moles Nb. No, you can't do like that, na? That is not the formula for a mixture of internal energy sorry, for the internal energy of a mixture of gases. No, that's not the formula. That is degrees of freedom of first gas into common pressure into volume plus degrees of freedom by 2. ऐसा कोई formula नहीं बोला है मैंने. कैसे आप लिख सकते हो ऐसा formula? See, for the final mixture, Samarth, what is happening is pressure into 2V is equal to nRT, where N is equal to Na plus Nb. Okay. And the total internal energy is Na into 3 by 2 RT plus Nb into 5 by 2 RT. This is logically how the internal energy is now. Because these many molecules exist at a temperature T and they have degrees of freedom 5. And these many molecules exist at a temperature T and they have degrees of freedom 3 or whatever. So when you correlate this with this, how can you write this as 5 by 2 P into 2E plus 3 by 2? ऐसे नहीं लिख सकते ना, ये statement ही गलत है. This statement is not correct because it's not in agreement with this now. The thing is that when you relate internal energy with pressure and volume, you are replacing nRT with PV. It's not the other way around now. Okay, so that was the solution of this question. Now let's come back to first law of thermodynamics. So from the fact that first law of thermodynamics applies to a thermodynamic process for an ideal gas, so an ideal gas is one which will always be related, which will agree with the equation of state for an ideal gas. So a thermodynamic process is one in which state change occurs due to exchange of heat and or mechanical work. So the experimental representation for such a state change or such a thermodynamic process can be visualized like this, that you have some kind of a chamber in which you have a piston and you have some mechanism of supplying heat or removing heat. So you have a heating element and you have a piston. Okay, so by moving the piston, okay, mechanical work can be done by the gas or on the gas, depending on how we are moving it. Okay, and heat can be supplied to the gas or absorbed from the gas through the heating element. Okay, so coming back to our statement of the first law, that Q is equal to delta U plus W. So in this, Q is defined as the heat supplied to the gas. Okay. And W is defined as the work done by the gas. So now we'll understand how to calculate these two quantities, or at least in which case they will be positive and negative. Okay, so let's understand firstly about work done by the gas. Yeah, Viraj, just wait for some time, you will understand. So what is happening here is that suppose the gas is expanding. Situation where we have an expanding gas. The process is such that the gas is pushing the piston up and making it expand. Okay. So if the area of cross section of this is A, okay, then the change in volume delta V will be A into delta X. Or for a small change, we can say that the change in volume dV is equal to A into dx, where if originally this length is x, the volume of gas inside is equal to A into X. So the change in volume is A into dx. Okay. Now during this process, if the gas is at pressure P, the instantaneous pressure is P. So the force it is applying on the piston will be equal to pressure into area. Okay, yeah. So therefore, work done by the gas. Okay, that will be F into dx. So that will become P into A into dx. Okay. Now A into dx is nothing but change in volume. So work done by the gas is P dV. This is work done by the gas for a small change in volume dV. Okay. So therefore, the net work done by the gas will become integration of P dV from initial to final state. Now, likewise, you can also see that if we are having a situation where the gas is being compressed because of some external agent pushing this down. So some external agent is pushing this down and compressing the gas. So during this time, what will happen? The force that the gas is applying, okay, is still doing, is now doing negative work. So here you can see that work done by the gas will be minus F dx. So that work done by the gas will still be P dV only. Okay, but here PV is negative of A dx because the volume is changing by a negative amount. Here it is positive because the volume is expanding. So dV is a positive quantity, whereas here this is negative because the volume is compressing. So work done by the gas is minus F dx integrated. So that will become again P dV integrated only, but this will come out to be a negative quantity because the volume is decreasing. So whether the gas is doing positive work or the gas is doing negative work, the universal formula for work done by the gas is given by integration P dV. And this quantity automatically it becomes positive for an expanding gas and becomes negative for a compressing gas. This is the general formula for work done by the gas. Okay, so hope the concept of work done is clear to you. Whereas as far as heat is concerned, if during a process what is happening is heat is being supplied to the gas, then Q will be positive. Whereas if heat is being absorbed from the gas, then Q will be negative, because Q is defined as the heat. It's actually defined like the net heat supplied to the gas during a thermodynamic process. Okay, next up, let us understand the graphical representation of a thermodynamic process. So the graphical representation is generally done in a PV graph. So if you look at a graph of pressure versus volume, P is the pressure, P is the volume of n moles of an ideal gas, and that one is the one undergoing a thermodynamic process. So the first thing we need to understand that any point on this graph actually represents a state. It represents a unique state. So let's say this point A has a pressure PA, it has a volume VA. So it also represents a temperature. Any point on the PV space represents a unique state of the gas. So for example, at this point A, there is also a particular temperature of the gas such that at the point A, the pressure, volume, and temperature are linked by this unique equation. Yeah, we will come to that. But see, to understand thermodynamic process, first of all, you need to understand PV graph. Okay? That's the primary type of graph. Now, suppose we have another state here, B, which has a different pressure and different volume. So automatically it will have a different temperature. Now, any thermodynamic process taking you from A to B will be represented by some kind of a curve. So any process from state A to state B will be represented by a curve from A to B in general. Okay. Now, if that curve is a horizontal line, it will become an isobaric process. If it is a vertical line, it will become isochoric. If it is hyperbolic, become isothermal. We'll come to all those things. Okay. But in general, I'm saying you're going from any state A to any state B through a particular type of process where heat exchange and mechanical work exchange is happening. So that process has to be represented by some kind of curve or some kind of path from A to B. Okay. And such that during that path, Q will be equal to delta U plus W for the process A to B. This is the first law of thermodynamics. So during that process, whatever is the net heat supplied will be equal to the change in internal energy plus the work done by the gas. Okay, now in terms of graph here, you can understand that gas is integration PdV. So in terms of graph, it becomes area under the curve A to B for the process A to B. So for example, if A to B is represented by this kind of a curve like we've done in the above case, then this area, the work done will be that area with a positive sign because you can see expansion is happening. Whereas on the other hand, if A to B is like this, suppose, then here you can see there's a compression occurring. So here work done from A to B will be negative of that area because there's a compression occurring. Volume at B is less than volume at A, whereas here there's an expansion occurring. So remember, when a gas expands, the work done by the gas is positive. Or we can even have a situation where the work done is zero because the volume does not change. We can have a process which is a vertical straight line like this from A to B. So there is no volume change. Later we will see this is defined as an isochoric process. So dV is zero. So work done by the gas is zero because the area under the graph is also zero. So by these examples, we can also understand one thing, that since work done is a path integration, or it is area under PV graph, work done is a path dependent quantity, or what we call a path function. Because for two different paths between the same initial and final state, the work done will be different. If we go from a certain state A to a certain state B by two different processes, let's say this is process 1, you can see the work done will be this whole area. But if we were to go by a different process, see the work done will be a lesser amount of area. So work done by process 1 is not equal to work done by process 2. Okay, so it is path dependent. So this is the second thing that we learn about work done. The formula for work done in general is integration PdV, or area under the pressure versus volume graph during the thermodynamic process. Okay. But the second thing we learn is that means that work done is a path function or a path dependent quantity. Okay, so work done becomes a state function. Sorry, becomes a path function. Now, next thing, delta U, the change in internal energy. Okay. Now, this from kinetic theory of gases, we have understood that internal energy of a gas is the total kinetic energy of its molecules. Okay. Of an ideal gas, that is. So that internal energy was given by the formula. Therefore, during a process, a thermodynamic process A to B, delta U will be nothing but okay, or in general we can say that delta U is NF by 2R delta T. So you can see that it is a state function. It is independent of path. Because it's path independent. So whether we go from the point A to B by process 1 or process 2, it's not going to change the value of delta U. Whether we go by this process or we go by this process, you're changing the state from A to B. So delta U is going to be the same formula, both the processes. This is for any process or path from A to B. Okay, so we can also relate it in terms of the product of pressure and volume, because PV is equal to nRT. And of course, keep in mind the standard values of degrees of freedom is 3 for monoatomic gas and 5 for diatomic gas. Okay, so now the third quantity, the heat exchange, you can see it is the sum of a quantity which is path independent and a quantity which is path dependent. Okay, this is a path function, whereas this is a state function. So since Q is the sum of a path and a state function, therefore Q itself becomes path dependent. Okay, because it's the sum of something which is independent of path, but another quantity which depends on path. So obviously the sum overall will become path dependent. So Q is a path function. So let us understand this with an example. Suppose a sample of oxygen gas is taken from state A to state B, which I'm showing over here. From a volume of 2 liters to a volume of 5 liters. The pressure here being 1 atmosphere. Pressure here being 2 atmospheres. But it is taken through a straight line path. So the process is like this. So take 1 atmosphere to be approximately 10 raised by 5 pascals. So a sample of oxygen undergoes expansion by the process AB as shown. Okay, find Q, delta U and W for the process. Okay. Secondly, if temperature at A is 200 kelvins, what about the temperature at B? Okay, just try out this question. Okay, so anybody got the answer for this yet? So we can see that since we are talking about oxygen gas, so it's diatomic. So degrees of freedom is 5. Okay. So the formula of internal energy is ten minus 2 liter atmosphere. And we can see that 1 liter atmosphere is equal to 10 raised power minus 3 into 10 raised power 5, or 10 raised power 2 joules. So delta U is becoming 2000 joules. The first thing, the internal energy is increasing now. Also, you can see volume is expanding, A to B. So the work done will be this area with a positive sign. So area of trapezium, so work done by the gas during this process is becoming 450 joules. So Q so these many joules of heat has to be supplied to the gas to undergo this particular process. Okay, people, so hope this question is fully clear. So with this, we conclude today's session, and we will continue with more examples, and we will look at the applications of first law of thermodynamics into the four particular processes. The named process is called isothermal, isochoric, isobaric, and adiabatic process in the next time. So that's it for today's session, people. Wish you all the best.